Hi all, it's Mr. Yeager for Physical Science, and we are beginning our unit on solutions. Trying to get that thing out of the way, go away, there we go. All right, our unit on solutions. So we've talked about solutions before back in the matter unit. We just mentioned, like it says here, that they're homogeneous mixtures, so we're going to kind of review that. But then we have to get a little bit more detail in describing these things. The reason is, in chemistry, we often put chemicals into a solution form before we start chemically reacting things. I mean, if you think about it, solutions are just something so common where we mix the chemicals together, they don't chemically react until maybe I then mix one solution with another one and then there's a chemical reaction that occurs, okay? So these are very important substances, so there's a lot more to it than just saying they're homogeneous mixtures, okay? So here we go. So, again, some of this review. We talked that solution is made up of a solute and a solvent. Okay? Solute is, again, what is added. Okay? Solute is what is added. And then solvent, we often just say, is the dissolving agent. Okay? Which basically means it's what does the dissolving. The most common solvent, water. Okay? We often have water as our most common solvent, as you can see down there. Down here, I have actually, I think that's copper 2 chloride. And then that's added to water, and then we're forming a solution of copper 2 chloride solution. Okay? And again, the copper chloride and the water don't react. They just dissolve. It's a physical change occurring. All right? And then we're trying to put as much of that solute into the solvent. Okay? So solute, solvent. So here's just some examples. If I said, okay, identify the solute and solvent. Okay? What I'd have here, right here, orange juice. Basically, orange would be my solute, okay? And then water is my solvent. Basically, I'm mixing, usually add some water to it, okay? I usually put some water in. Obviously, you always say there's pure orange juice, all right? But a lot of times there's a little bit of water that waters it down some, so it's not so concentrated, okay? What about the ocean? That's a pretty simple one. There's salts. That would be our solute. And then water is my solvent. You're going to see kind of a theme here. Okay? There's only one in here that's not going to be water as a solvent. Soda, okay? I mean, we could talk about carbon dioxide, basically carbonation, okay? B is a solute. There's a whole lot of other stuff, obviously. I mean, there's a lot of different ingredients that are dissolved and all together. It's not like there's a chemical reaction that creates Coke, okay? There's probably a licorice flavor that's dissolved into it, other things like that. Cherry Coke, there's going to be a cherry flavoring put into it. Again, all this ends up basically just being mixed into water. So water is my solvent. Okay. The last one over here, I actually have different oils. Okay. And I mean, in this case, maybe it's like you have some olive. I mean, you have a different type: olive oil, avocado oil, and stuff like that. But that would probably be. Olive oil is maybe my solute, and then maybe some sort of like vegetable or canola oil is helping dissolve all that stuff together, okay? So that would actually be a case where water is not the solvent. If I put water in it, it's going to stay separated. You're going to have a suspension and not a solution. So there's different types of solutions out there, all right? They're not only liquid. Liquid's the one we all think about because that's what we see when I say what's a solution, you're usually going to think about liquid solutions. So there are liquid solutions. You can see the different basically coloring dyes in the water, and then as we already said, orange juice and water, okay? But there can be gaseous solutions. Air is a mixture of gases, and again, it's a mixture of nitrogen, oxygen, argon, other gases, carbon dioxide, water vapor, all right? That gas is a solution as well. They don't chemically react, all right? They're all just mixed together and we can't tell. We don't say, again, that there's oxygen in that corner, there's carbon dioxide in that corner. It's all mixed uniformly. There's also solid mixtures, all right? While not like something that really comes up on our EOC, we always call solid solutions alloys, all right? There'll be alloys. So basically, I think I have brass right here, which, and I might be wrong, I believe is copper and zinc or something like that, all right? We got bronze over here, all right? Unfortunately, I don't even remember what two. It's copper and Copper and something else. I forget what the other part is. Copper and another element. Sorry, don't remember. And then we got steel right here. Okay, steel is obviously mostly iron, but then if it's stainless, there's chromium, and other elements might be in it as well. So we can have solid, liquid, or gaseous solutions where it all looks like one entire substance. So, what does it actually mean? This is now where we're getting into a little bit more detail than what we did with matter. Okay? What does it actually mean to dissolve something? What is dissolving? All right? It is the process, as it says right here, of the solvent surrounding the solute and making it disappear. Quote unquote, that's again, quote unquote, disappear. It's not actually disappearing, it's just if it's surrounded by the water, we cannot see that other chemical anymore. It's all mixed in completely with it. All right, we know it's there because we could taste it or something like that, but it's basically the water, it will surround the solute, it'll possibly split it up into ions, and then you can see here where the water is all surrounding the sodium, and then over here, this is a good picture of the water coming in and slowly trying to separate out those ions of that sodium chloride, that salt, okay? And the more and more it does it, the more that surrounds it, the less you're gonna see. It's still there, again, it's still there chemically, but you can't see it anymore. And, oh, sorry, that's called, in the end, solvation. Okay, so solvation is the process of dissolving, all right? When you're mixing in Gatorade powder, you are doing the process of solvation while you're mixing that powder on into water. So, how do I know the substance will even dissolve? Well, we have a very simple rule. We just say, like dissolves like. Like dissolves like. Okay? And what does that mean? We're going to see in a minute. I mean, we got a funny little cartoon here. Bears are insoluble, meaning they don't dissolve. But this one's saying, no, you know, that's easy for you to say. You're not polar. Okay? Probably have no idea what that means until we see this. Okay? Like dissolves like means it depends on whether the substances are what's called a polar or non-polar bond. Okay? Polar or non-polar. Polar and ionic go together. They're not the same thing. They're not the same thing. But ionic and polar have a similar property in terms of it has the idea that the charges are not completely shared. Okay? So it turns out the different substances out there can be classified as either polar or ionic or non-polar. Okay? Ionic and polar are going together for our problems here. So polar substances are substances that have at least some little bit of charge. All right? It turns out polar bonds, they don't share electrons equally. Okay? So obviously with an ionic bond, ionic is basically the extreme example of a polar bond, where they're not even sharing them at all. There is no sharing. But it turns out covalent bonds can have this partial sharing, which means that one substance might be a slight charge, while the other one, it will be a slight opposite charge. Okay? So polar are things that have a slight charge. Way I need you to understand this more is that they will tell you that the object might be polar or nonpolar, and that's how we're going to use to describe whether the objects dissolve. Nonpolar substances is anything that they share completely, and there's absolutely zero charge between the two. So like dissolves like means polar dissolves polar, polar dissolves polar, and nonpolar dissolves nonpolar. If you mix polar and nonpolar, they will not dissolve. They will not mix. You'll form a suspension. Okay? You'll form a heterogeneous suspension. But polar and polar will mix together, nonpolar and nonpolar mix together. Again, this basically includes ionic. Okay? That basically includes, polar includes ionic. All right? So, examples, well actually I want to say this. The most common polar chemical is water. Water is polar. So that is probably something to make sure we know. Water is polar. Oils are generally non-polar. Okay? So water is polar. Things that are oily are definitely not polar, non-polar. So examples here would be, hey, I have lemon juice and water. So the question might be, we know water is polar, so what's lemon juice? Well, lemon juice will dissolve in waters, which means lemon juice must be polar. Okay? I have over here water, and I have some salts. It turns out the salts will dissolve, which means the salt must be polar. Okay? Water is polar. Right here I have some oil, some vegetable oil. It is not dissolving. That means the oil must be non-polar because the other substance in there is water. Okay? So this would help us understand whether something should or should not dissolve, and then we can obviously test it to confirm it. Okay? So like dissolves like, polar dissolves polar, non-polar dissolves non-polar. What will affect how quickly something will dissolve? All right, there's 3 things you can do to try to increase the ability of something to dissolve. All right, that would be stirring, or what we sometimes just call agitating the solution. All right, we can mess with the surface area, meaning is it easier for the substance to dissolve when crushed, or can I keep it in a block? Will it dissolve really quickly? And then the last one is temperature. Okay? So stirring, surface area, and temperature will all affect how quickly the substance dissolves. So going through that, why would stirring or shaking help the substance dissolve? It's because you're moving those particles around each other more. Okay? The more that you move them, it allows the water to basically get a little bit more, I want to say energy, but it allows them to get around that solute and possibly dissolve it a little bit more, which is why, again, we shake things, okay? If you just dump a bunch of powder in, it all might sink to the bottom, and then only little bits of it is being dissolved at a time. I mean, it should eventually all dissolve, but it has to wait for those water molecules to come down, hit it, and spread them on out. So by stirring or shaking or agitating, that'll speed up the process. What about surface area? Smaller particles that are spread out will dissolve more quickly. So what does that mean? If I increase surface area, I increase the rate of dissolving. Things will dissolve again faster. All right. So what I have here is basically sugar, crushed sugar, and sugar cubes. Which one's going to dissolve faster? The crushed sugar. Okay. The crushed sugar. To get something to dissolve faster, the more spread out it is, the faster it will actually dissolve. It turns out that's why like liquids and gases actually will get absorbed faster because those particles are completely separated. Okay? So things that are crushed, it takes a lot longer. All right? Medicines, again, they like to put them in the capsule form because then it slows down that dissolving rate of it and doesn't let and obviously it's also to make sure it can get through parts of your body, but that'll help slow the process of it being distributed into your body and possibly acting too quickly. Okay? So we want it to be, if we want it to dissolve quickly, we have to spread it out more. Temperature. Okay? The last, and this is one that we're going to talk about a lot more in another video, temperature plays a major role in how well things dissolve. All right? And so with temperature, it's sort of like the agitating, but now you don't have to actually stir it. If you increase the temperature, we already know that means you're going to increase the kinetic energy, which means the particles move faster. Okay? And what that means is those particles, like the water, the solvent, and the solute, they're able to basically get surrounded faster. The solute's able to surround, the solvent's able to surround the solute faster. This is true for solids and liquids. Okay, basically all solids and liquids. It turns out, if this might be on the next page, if you increase temperature, you actually decrease the rate for gases. Okay, they don't do it as quickly because actually it's more difficult to then grab them. Okay, they're moving around too fast almost. All right, but this is why if you're making iced tea, a lot of people basically boil the stuff first, add the sugar, add the tea leaves on in, so that more will get dissolved very quickly, and then you can cool it off. then it gets cooled off. Same thing with like hot chocolate and things like that. You always heat up the water, add in the coffee grounds or hot chocolate, and then it dissolves much more quickly. Okay. As I said, I knew I had it. I thought I had it. Gases and temperature. The only opposite about this is gases. Gases, if you increase temperature, you actually decrease the gas that's dissolved, and that's because those gas particles basically are moving quicker and can actually jump out of the solution. This is actually the bad case of thermal pollution, where if factories dump out a lot of hot water, they don't think it's causing any issue, but that'll reduce the amount of oxygen in the water, and that can actually kill fish and change the ecosystem that's in that pond and cause some major problems. Okay, so that's where I'm going to stop. I'm going to do another video on continuing the solutions, but we're going to focus on the measurement of solubility and having to break down those solubility curves. But in this lecture, we basically, again, went a little bit more detail of why are solutions formed, the idea of solvation. We looked at, what substances dissolve what, like dissolves like, and then the three main factors, stirring, surface area, and temperature, that will affect how much gets dissolved. But that'll be it. Thank you.